Okay guys, in this video here I'm going to walk you through how to do assignment 8, our final assignment for the semester, in case you haven't been able to figure it out on your own. So what you can see here for task 1 I've got is these statements I want you to run before you execute any of the procedures. And you can see we're looking at statistics on our columns, and we're also looking at our user tables to see if statistics have been gathered. And what you can see when you look at a number of these columns here is that the database has not gathered the statistics on the tables. And what that means is it doesn't know anything about the data that is contained in the tables that will help it decide the most efficient plan to use to fetch the data. So now if we run our gather statistics procedure in this this little bit of PL SQL that I've given you, this will cycle through the tables that we created in assignment 7, and once it's done we should be able to go back and have a look at the statistics tables and see that the system has actually gathered statistics. So this takes a couple of minutes to run because some of these tables are pretty large, and it has to go through and count the rows and do histograms on the values inside of the columns in order to completely build the statistics. So this will take a minute. One thing we'll see after this is completed is we actually need to be able to grant a number of permissions to the user, in your case I think user 7, for this assignment in order for the user to run an explain plan. And in just a second here I'm going to show you how to do that. But the basic procedure for running an explain plan in SQL Developer is we can highlight a SQL statement that we want to do an explain plan on, and we can right click it, and then we can see that we have this ability to explain up here. All right, so our PL SQL procedure is completed, so it should have gathered statistics on all our tables. Now if we come back and have a look at our statistics tables, we should actually get some results from them. So we see now that it's gathered a bunch of information about the columns in our tables, and if we take a look at our user tables, we should also see that a number of statistics have been gathered on the tables that we've created here. And so this allows the optimizer, which is really the secret sauce for the Oracle database, to build the most efficient plan. And then interestingly, if you want to do this iteratively, there's actually a procedure that you can run called the delete schema stats, where I can just delete all the stats for in my case this 4.7 user and schema I'm using, and then I can run this stuff over and over to see kind of what's different if I want to do that. In any case, for our purposes, I've already granted all of these permissions right here to my user, which means I should be able to effectively run a explain plan. So if I highlight this and click explain and then explain plan, I should get an output down here which gives me a sense of what the cost is. Now cost is really you know, sort of a value without any particular units, right? This means something to the optimizer, and the general rule on cost is a higher cost is worse, right? So when we're doing SQL tuning, we're always trying to minimize the cost for the optimizer. So if we're going through this iteratively, we might be we might be looking for this cost to go down in particular spots. Now you can see here when I'm running an explain plan that we see this in-memory full is going on here. And so I actually have these tables in memory at the moment. So they have a really low cost because we basically dragged all of the information into our RAM on this machine, which is essentially one of the fastest ways we can access it. We've also done what's called a columnar almost transformation. Instead of the data being stored in a typical row format like we might think of normally, it gets pivoted and stored in a columnar fashion, which is a much faster way to access the data. Now there's a number of databases that kind of specialize in this particular operation called, columnar databases. What's very nice about the Oracle database and this version of it is when we place a table into memory, it keeps track of our table in its typical row-wise fashion that we would be used to for any relational database, but then it also transforms those tables into a columnar format as well, and that's all transparent to us. So the database will do all of the heavy lifting around keeping those two different formats in sync with each other. When this is typically, more of an ETL operation when you're trying to do it a different way, but the database makes this all automagical for us. So I can actually scroll down in the SQL that I have here, and if we scroll down, we can see how I've actually put these tables into memory. So I have these statements here, which basically says alter table and put it in memory. And then I can also take these tables out of memory. So I should be able to run all of these, and we can see that they've all been altered, and that should take them back out of memory and should actually make our explain plan more expensive at this point. So if I scroll back up, which I will do right now, we can go back up and run an explain plan again on our statement here. So I'm going to go ahead and do that. And we can see now that I've taken these tables out of memory that it's quite a bit more expensive in operation. And basically what expensive means is it takes longer, right? It requires more resources from the server in order to answer the result from this query. So now here I have this ability to try creating some different type of indexes. So I'm going to create an index here, and one, I'll make sure that this index doesn't exist already. So I'm going to drop that index. Then I'm going to run this index again. And it's barking at me here because I'm trying to put this thing into a table space that doesn't actually exist at the moment. So I'm just going to get rid of that table space clause. And then we'll give this a second to run, and because this is a pretty large table, we'll see that it takes a minute to run. And so what I've done here is I created a standard B tree index, and if we take a look at this and we run an explain plan, we'll see that our cost on this particular query hasn't gone down any. Because for whatever reason, essentially the optimizer is still choosing to do a full table scan. Now if I drop this index and I try to create a different type of index called a bitmap index, we can run this, and again it'll take a few seconds to do because this is a pretty large table, but that was quite a bit quicker that time around anyways. And now we can come up here and examine this one more time to see if that index made a difference on it. And here we can see that this cost number has actually gone down a fair bit by putting what's called a bitmap index on it instead of a standard B-tree index. And a bitmap index is a special type of index that's really meant for data warehousing purposes. And it converts, basically the way it works is it converts the values in the index into what is really a bitmap, ones and zeros. And then when you have several of these indexes on a table, before it goes and fetches any of the results from the big, what's typically known as a fact table, it will combine the results of all the bitmap indexes together to filter down to the very limited row sets that need to be returned, and then it'll go out and fetch those from the table. And that's a very efficient operation when you compare it to other ways. So if you're interested in knowing the difference between the bitmap indexes or standard index, then you're more than welcome to go and read some more about that. So the next thing we want to do is try running some different type of indexes here. So I'm going to go ahead and drop this index that's most likely already been created. And then we're going to do an explain plan here where we're joining to a different table. Still, we have our large fact table for our data warehouse here. And this is what's known as a date dimension table. And we're going to run an explain plan on this thing. So if we run an explain plan, we'll see that it gives us a cost. It costs $73.48. If we go out here and create an index on this table, standard B-tree index, again, it's complaining to me about this table space that doesn't exist, so I'll just skip the table space piece of that clause. And so this first pass through takes a couple of minutes, or well, maybe not a couple of minutes, we'll take just a few moments here as it goes through this large table and creates this index on it. And now if we come up here and we take a look at the explain plan again, we'll see that it hasn't really changed, right? So, what the purpose of an index is on a table in a case like this where we have a predicate or a where clause, we know that we have like 100 years worth of data in this table, and what we want the index to do for us is to really make it quicker and easier to go fetch this particular year's worth of data. And if we have an index that the optimizer thinks is worth using, then typically this will, the accessing the index will be much quicker than performing a full table scan on this large table. But for whatever reason, without the use of a bitmap index here, it doesn't seem to want to do that, and it's doing a full scan of the table. So we're going to go ahead and drop this index and create another bitmap index and see what the difference is between the cost. So, it dropped the index for me. Still mad about the table space that doesn't exist. I'm going to go ahead and create this. And we'll just give it a minute. We can see that that's been created, and now we can go run an explain plan on this particular statement one more time. And okay, now that we've done that, we can see in this particular case that doesn't seem to have helped us out any at all. So we have the same case or the same cost showing up for this particular table, and sometimes this can be a function of how many values are in the underlying index. We know that this date index is actually, or this date table is actually quite large, and so for whatever reason it may not actually be giving us any benefit here. But now as we go down through here, we can check the values. We can sort of keep iteratively going through, and as we build more complex statements here, we can keep checking to see what the result of the various indexes are on the total cost of the statements that that we're building. And this is kind of a sort of a trial and error process, and something that a lot of DBAs might be engaged in typically in their enterprises, as people complain that a particular SQL statement or some reports is running very slow. So you'll typically go get the SQL that's being generated by the reporting application or whatever application that's having the issue, and then you'll come out here and you can run some of these explain plans, try some different indexes, and try and reduce this cost and speed the time that it takes to return this information ultimately. So I'll leave it to you guys to go through the assignment and try these, creating these indexes and trying the different explain plans. Ultimately, where you should end up as you come down through here is you should end up with a number of these bitmap indexes created on your tables, and you should ultimately see that the explain plan on the final statement is quite a bit quicker than it otherwise would be. Now, in the assignment, I think the last thing we do is I'll have you put all of these tables in memory and then check the differences between what happens when you build indexes and what happens when you put these tables in memory. Now, as you go through and you add indexes, you'll see that the the cost shown by the explain plan goes down a fair bit, and you can make your statements quite a bit more efficient. But none of that will compare really in any way with placing the tables into memory with this in-memory statement, because this is really substantially faster than basically anything you can do with an index, because it essentially eliminates all the I/O or the trips back and forth to the spinning disk that you would typically make with a database that's using some type of storage device. This is the in-memory, places it directly on the random access memory for the server, and in a typical scenario, you would have a server with a very large amount of RAM, and this would allow you to drag literally terabytes of data into the sort of fastest storage that can be accessed with your server. So this is a great new functionality that is being implemented really across a lot of different database platforms, but it's really just recently begun to kind of revolutionize what we can do with relational databases, because it makes it easier and easier to leave our data in kind of its raw format and still be able to access it pretty efficiently if we're dealing with, say, ERP systems that have just transactional tables. And then in the case where we have very large data warehouses, this also gives us the ability to vastly improve performance by placing these tables in the memory and allowing the database to fetch the results many times faster than it would be able to with the typical storage scenario. So when you're all said and done, you should just have to run these statements, which will show that essentially you have created the indexes and tables that I've wanted you to do. This will essentially allow me, and don't pay any attention to what's necessarily on my screen here, but this will allow me to see that you've collected the statistics on the tables that you were meant to, and also whether or not you have been able to successfully place those tables into memory. And in my case, I've taken them out so you can't see that they're there. But were I to go up here and alter all of these tables and place them in memory, and then come back and run this statement, we would see that I can actually see that they've been placed into memory. And then this last piece here just allows me to see that you've gone through and you've created a number of indexes on the tables, and specifically the ones that I wanted you to create as part of this assignment. So that ought to help you get through your final assignment. Of course, if you have any questions, you're welcome to call me or reach out to me. I'll try to make sure I'm pretty attentive here in this last week or so of class, because I know you'll all be wrapping stuff up. And hope everybody had a good semester and is able to wrap up the rest of their classes successfully. And have happy holidays. And I hope you enjoyed the class. All right, bye now.